Today we're going to be talking about acceleration of gravity on a flat Earth and on a sphere. So we're going to look at it the way it's described in the heliocentric globe model of Earth, and then we're going to look at how it would work in a flat model and how orbit like ISS, Starlink, things like this are possible on a flat Earth. And I think that they're more possible on the flat Earth than they would be a sphere, and it doesn't take a change in thinking. So what I want to imagine is we're looking at the spherical Earth here, and if we look at gravity on a sphere the way it's described, you have all of these vectors that are pointing to the center. Okay, so all of the vectors all the way around the surface are going to be pointing towards the center. At the center, there's an equilibrium of gravity. This is the first thought experiment that we're going to do to show that it really doesn't make sense with everything being pulled to the center of a sphere, that there probably is another mechanism responsible for what we're measuring, even in the sky, with what we're considering that mass is attracting mass. We'll go into that in a little more detail. But if we're imagining gravity pulling to the center of a sphere, and you're in the center of the sphere, it's theorized, it's a theorem, that you would basically be floating, because you're in the center of all of these gravity vectors, right? You're at the center of mass. But when we do the thought experiment, it really doesn't make sense that way. And the reason why is because once I'm in the center of the sphere, right, gravity would be pulling me in all different directions, right? I would be being pulled in this direction. I would be being pulled, depending on what vector we're talking about, being pulled to the center. It would be the opposite of that if I was in the center. So if we imagine this, you would actually be ripped apart in all directions, because if you're in the center of a sphere and mass is attracting mass, you're the mass at the center, and if you draw a line from the center to the edge, you're going to be attracted by all the mass from here to here. Right? And that's not how gravity is measured. Gravity is measured to the center because in the beginning, when the accretion disk was moving around the sun, all of these particles were attracted together and they made these spherical bodies. Right? That's the way that it's explained. But when we think about it, gravity should actually be measured from edge to edge, the way that I'm visualizing it, because if I'm standing on the top and gravity is a vector that's pulling me down, so if I'm standing here, gravity would be pulling me in this direction. I'm not just being pulled in this direction to the center. There's all this mass on the other side of the Earth, right? So if Earth is a sphere, I don't just have the mass of the Earth that's attracting me to the center. If mass is attracting mass, it's attracting me to the edge. So I should be measuring gravity from edge to edge. So that is one thought experiment, and there's more than one way to look at it. I understand that, but that is, to me, the most simplified way to look at it. Instead of saying there's this magic pocket of equilibrium in the middle of a sphere that you're just going to float around in if you're in the center of the Earth, I think it would actually work the opposite way, because we can prove with the Cavendish experiment, with scale, with everything else, with lead balls, like if you use a torsion and a scale, you can prove that mass attracts mass. So if mass attracts mass and I'm at the center of all this mass, I'm going to be pulled in all directions. I would be ripped apart. And that's not the way that we imagine it, okay? So when we're thinking about vectors, when we're thinking about the acceleration of vector of gravity, it's important to remember that this is different than the velocity vector, right? The velocity vector is moving perpendicular to the gravity vector that is an acceleration vector to the ground. So if we imagine that we're in an airplane, and inside of the plane we're going to base the gravity vector off of the center of mass. And when we define the center of mass, because we're moving at a velocity in the plane, we can't line this vector up directly with the ground. And the reason why we can't do that is because if I shut off the engines in that plane, the plane isn't going to fall straight down to the ground as if it was affected by gravity. And I realize that a plane has wings. You're going to have a different equation determining the parabola or the arc to the ground on a plane than you would a ball, right? A ball is a spherical shape. But if we do a thought experiment with the ball, if I was able to hit a baseball at 500 miles per hour into center field, and I was able to put a force field around the ball that would cause the ball not to be affected by any of the atmosphere or by anything that would interact with it, what is there to slow that ball down? Nothing, right? I mean, if I hit a baseball, the initial contact of the bat we know is counteracting gravity because the baseball is going up into the sky, right? It's pulling up against that vector, and if the vector was pulling that ball straight down and we were to draw based on the force where that ball is going, it would fall straight to the ground. You would never be able to have any forward momentum. Imagine running in a race and tripping over something, right? You're going to fall forward and roll forward. Now imagine being on a motorcycle and hitting something. You're going to fly off the bike and you're going to move forward that much further. Imagine traveling in a plane at 500 miles per hour and shutting off the engines. When you shut off the engines, you got to consider the lift and the drag and all of that other stuff as far as how fast you're going to fall to the ground, but I'm not going to be pulled straight to the ground. So if we consider the center of mass and velocity, velocity is always carrying us ahead of the center of mass, right? Depending on how far ahead of the center we are, based on the velocity, depends on how stretched this vector is. If this is the plane, then this would be the ISS, way even further, right? When we consider the plane, the speed of the plane and the speed of the ISS, gravity would be, because it's being stretched, it would be bent, right? But it would be pulling in this direction. And eventually, I would be moving so fast where I have gravity pulled in this direction. But that's not the way that it's described on a sphere. On a sphere, when we're thinking about gravity, we are falling. If this is the ISS, gravity is pulling me down at 8.33 meters per second squared, and I'm continuing to fall around. So in the heliocentric model, the acceleration of gravity is also described as a change in direction, right? Because if I have a tangential velocity moving out here towards the edge, gravity is perpendicular to that, right? It's pulling straight down in every direction. So if we think about it like that, what I'm doing is I'm falling at the same altitude, right? I'm not ever getting closer to the ground because I'm falling around the surface. Now, here is where the problem comes when we consider gravity as an acceleration vector. It's explained that the forward momentum, the velocity of the ISS at 17,500 miles per hour above a sphere, is perfectly balancing the acceleration of gravity, right? But when we think about this in terms of the way this is working, if the ISS is moving at this velocity while it falls, the question is, what is causing it to fall slower, right? What is causing it to not accelerate? Because we're just falling. We're really not moving. If I change the vector, which it's kind of confusing because I had it straight, but the ISS is falling at the same rate and at the same orientation, right? As it's falling around, it's falling at the same rate and it's falling at the same orientation. So we can imagine that you would be associated with gravity in such a way where your forward momentum is counterbalancing that when we're thinking about, for a second. But the next second, it's accelerating. The next second, it's accelerating, right? You would have a perpetual acceleration, and the way that I imagine it is you would perpetually accelerate into the surface. But that's not the way it's described, so we're going to keep everything with the way that it's described on a ball earth. We're going to move the ball out of the way, and we're going to focus on the way that gravity works on the flat earth. So again, if we consider the velocity vector to the ground, or the acceleration vector to the ground, which is accelerating, and we consider the motion of the ISS in the higher atmosphere where there is no atmosphere. So do I need wings to generate lift? Do I need wings to generate lift if there is no atmosphere? Of course not. I'm already up there, right? I don't need to generate lift. There's nothing to slow me down. There's nothing to make drag. There's nothing to pull me towards the surface. If I'm traveling at 16,500 miles per hour over a flat Earth, which is what the velocity would be, and we could measure that, because if we consider that the Earth is a ball, right? Let me show you this really quickly. If I consider the Earth as a ball, I need to put a chord to the center, or I need to consider the tangent, right? Because if I'm measuring the velocity of the ISS, I have to figure out what the orbit of the ISS is, right? So to do that, I've got to draw a chord down to the center, and we're going to connect that chord to the surface, and then I'm going to rise above the surface based on the altitude of the ISS, or the altitude of whatever object that we're talking about. And if we imagine like a tether ball, you can calculate based on that, the swinging of that ball around your head, what that orbit is going to be, and you can use that as a basis to calculate the speed. But if you don't assume that it's traveling over a sphere, you would basically have to know where that terminator is on the horizon, and you usually can't watch the ISS from horizon to horizon unless it's right at sunrise or sunset, because you have that flat Earth terminator, right? On the flat Earth, the terminator would be shaped more like this, right? It would be more at an angle like this, so you would have a terminator in the sky because of the way the model works. We haven't even really gone into that, but it would be at a shallower angle. On a sphere, your terminator is exactly what it is. I mean, on a sphere, it literally, if the sun is shining this way, it literally divides the ball in half. It is a straight line. The light cannot go beyond the edge of the sphere. Now, we do have an atmosphere, right? But if we're considering the atmosphere and the terminator of a sphere, you would have a little bit of an angle to the top of the atmosphere where you would see the sun a little further, but your angle is going to be much shallower, like what we observe on a flat Earth. On a sphere, it would be very steep. So you're talking about like 5 minutes after sunset, I would be able to see the light of the sun. Versus 2 hours after sunset, I can see the light of the sun after the sun has moved an additional 30 degrees. Right? It's a big, big difference. Okay, so let's look at how we break gravity on the ISS above a flat Earth. If the ISS is stationary, our vector is going to be pointed straight towards the ground. Okay, if the ISS is in motion, and we're considering the center, okay, so we're considering the center of mass being in the center. If the ISS is in motion, then again, it's moved out ahead of that center, because if I was centered with it, I would be pulled straight down. So we have to adjust this arrow. And the further I am ahead, okay, let's say we're way over here, the more this arrow has to be adjusted to match that angle. Now, do you see when the edge of that arrow gets parallel to the ground and it's like this? The velocity vector is overcoming this vector because this vector is so stretched out, you're not being pulled down anymore, right? And you are, but it's so incrementally unobvious, right? You would have to adjust your trajectory every once in a while. And that's what happens on the ISS. But there's nothing that can slow you down on the ISS. You're continually traveling. So if I open up the map that we're using to describe the flat Earth, hold on, I'll do that real quick. So if I imagine that the ISS is moving across the surface of the Earth, and I consider the motion of the cosmos, there's nothing to slow it down. But the motion of the cosmos, like it pulls the tides, is going to pull the ISS a little bit. So your orbital path, and I want you guys to notice the latitude lines here, right? If I'm moving in a straight line, what is the shape of this actually going to be? Right? If I draw the shape of it, it's going to look like a sine wave, right? Because of the shape of the latitude and the longitude lines that are below me. But I'm actually traveling in a straight line. I'm actually traveling from here to there. So if this is the ISS, this little arrow down here, and we're moving, but as we're moving, we're being pulled a little bit by the cosmos, like the tides, right? So on my next track, I'm going to come out in a little bit different location. I'm never on the ISS going to go south of 60 degrees. So we're never going to go south of this circle. You're never going to fly directly over Antarctica, and you're never going to fly directly over the poles. So if we take this circle around here and we imagine a circle up here, the ISS, the motion of the ISS is in between these 2 points, right? So, and even though it's traveling in a straight line, it's making a sine wave across the surface because the latitude and the longitude lines are drawn on the surface. That's why people say, well, it's impossible to rectify all this stuff unless you have a globe. No, it's impossible to rectify unless you have circular latitude lines with curved longitude lines. That's all you need. You don't need a ball. You don't need a convex surface. You don't need any of that, right? We can make great circles work on this map. Every great circle works on this map because if I'm flying from here to there, the latitude line is going to be curved, right? So that's going to make the path on a flat Earth from here to here, it's going to make it look like this. But we're actually traveling in a straight line. The only thing that's making the path appear to be curved is the lines that are on the ground. So when we're thinking about that, when we're thinking about the way that gravity would actually work, it's different and kind of fascinating when you think about it. Hold on, move that. All right, so now what I want us to imagine, we're going to imagine orbital mechanics a little bit. So we can see that if the ISS is at a tangential velocity, and it wouldn't actually be a tangential velocity, but it would be a velocity above the surface in this direction, and gravity is being pulled in this direction, eventually, if the acceleration here, straight up and down, is 8.66 meters per second squared, or 8.33 meters per second squared, whatever it is, the acceleration pulling this way is not going to be nearly that. And that's where the math comes in, right? That's where we're just explaining it in layman's terms. This is really a simple equation when you think about it, but using vectors really helps you to visualize what is happening with the ISS and what is happening with the vector of gravity. Now we have gravity accelerating in this direction with an object that's moving very, very fast in this direction. It's not going to have any impact on this. Okay, so what about when we try to fire a rocket? Okay, so if I was to fire a rocket straight up, what is the vector of gravity? Oops. Okay, what would be the vector of gravity? It would be pulling straight back down, right? So we're not perpendicular to the vector. We're not stretching the vector in another direction. If I'm firing something straight up and I shut off the engines, I'm going to fall straight down a lot faster than if I'm hitting a baseball across the surface, right? Imagine hitting a baseball straight up in the air, right? It's not going to go as high. It's not going to go as far because we're hitting it straight up. But if I hit it up this way and we stretch that vector of gravity out a little bit, the acceleration, you can get the ball to go 450, 500 feet, right? Just a regular batter can do that. And if we consider that we can make that baseball fly at 500 miles an hour with the force field around it that's not ever going to allow it to slow down, it's never going to interact with the air, there's nothing that's ever going to slow that baseball down, right? So we have this thought about gravity in our minds, and we should have that thought when we're thinking about firing objects straight up. Because when I run out of energy, what's going to happen? I'm going to fall straight back down to Earth, right? Now, if we think of a geostationary satellite and we think of the way that it gets into the higher orbit, as they call it, we're going to start off here, right? We're going to do one complete circumnavigation, and then we're going to change our trajectory a little bit, right? We're going to do another burn. And when we do another burn, it's going to take us higher above the Earth at an angle. So we're kind of perpendicular, but it's kind of in this direction, right? Because the rocket's not traveling parallel to the surface, it's traveling up in this direction. And As it does so, it loses speed, right? So I believe that there is an equilibrium pocket above the Earth in between the reset of the sky. We're going to talk about that more in the next video. But in between the reset of the sky and the cosmos that is actually below us, the sun and moon and stars are actually below. That's why they move the tides. That's why they cause the Coriolis effect. That's why we experience what we experience on the Earth. That could never be demonstrated on a sphere. The only way you could demonstrate that on a sphere is if you put a plastic covering over a sphere and you put another plastic covering that has like an inch gap or a couple of centimeters in between, and you connected those two together. You know, you'd have to physically connect them together with like posts or something to keep the structural stability. Otherwise, the sphere on the inside would bounce around, right? So you would have to have a structure to connect those together and keep a separation between them. Then you could fill it with liquid, right? And you could spin it and you could try to replicate the Coriolis effect the way we experience it, but that is not what the mechanism is, right? The mechanism is really simple on a flat Earth. A physics girl did an experiment with pole vortices where when you drag a plate through the water, those pole vortices are spinning in opposite way on each side of that motion, and that's where the majority of the motion is taking place on Earth, right? That's where the celestial equator is. That's where all the stars from both sides of that circumpolar rotation come together. In that 23 degrees on each side, that's where the sun is. In the 28 degrees on each side, that's where the moon is, because the moon is offset a little bit, and it moves a little bit further from our perspective than the sun does, or than the sun does on the other side. It's like a 36-year total cycle. I think it's 18 years in one direction and 18 years in the other direction. So sometimes the moon can set as far as 28 degrees south or 28 degrees north, right? When it's offset like that and you're at the end of that cycle, it can be off by 5 degrees more. But all of that motion is taking place in the center, and that's what we're experiencing as the Coriolis. And because the cosmos is under us, causing that, when you look at a geostationary satellite, it does this little figure eight Alima type motion in the sky when you're looking at it. And that's why, because the cosmos is moving, and it's drifting that satellite a little bit, but it's stationary. And it's not stationary. So in the heliocentric model, what's happening is Earth is turning, right? And as Earth is turning, you're putting the satellite at a point above the Earth where it is turning with the Earth, right? It's pretty much turning with the Earth. As the Earth turns, the satellite is moving at the same rate, and it stays pretty much at the same location above the equator. But the flat Earth, if we use vectors like this, it's very simple to understand why orbital mechanics works the way it does. And if we consider gravity, if the center of mass is pulling straight down, it's based on where the mass is in relation to the center of a stationary object, right? So that center of mass is always moving across the surface, but it's moving based on that speed, right? So if the ISS is moving, this is moving, right? But it's moving based on how fast and how far out of it the plane is, or the ISS is, or whatever else. So we're putting that center of mass behind the moving object, because if it was directly underneath the moving object, whether it was in motion or not, would come straight back down.